Yeah, so it's very fascinating. Like I said, there's a lot that you can look up about this, and there's some people that have vertigo spells quite frequently, and they'll have to go into a specialist to have them try and reposition the crystal or something that's causing the dizziness, and that's the Dix-Hallpike Epley maneuver that they were just talking about, which is a whole another topic, but it's very fascinating though, so I'd say look it up.
Or if you're really interested in balance, just join the CSD major because balance is included in all of that.
Yeah. All right, so then we'll go into the inner ear. So this is the cochlea, and the goal of this is to send auditory information to the brain. And I thought this was a super cool picture. I believe this is in a rat, possibly. So you see the cochlea here. There's 2.5 turns for the complete rotation. And within this is the basilar membrane, and it's tonotopically organized, which basically means where high and low frequencies are located. We won't go into super great depth about this as well. However, so this is the basilar membrane, and this is located within the cochlea where this line is.
And we have some really cool videos for the cochlea because it's so small, but it does so much. It's really fascinating.
Yeah. So, yeah, please do.
So you guys remember when we were talking about when Dr. Bennett and Jasmine were here about like finding your passion and you see something that just excites you and you're like yeah,
that's it.
now I know I'm a speech pathologist, or now I know I'm an audiologist. If you saw that and you were like, wow.
Come talk to us.
It's your thing. Be an audiologist.
Yeah.
Yeah, it's just so cool because it's just such a unique system, and as we're talking right now, your ears are doing all of these things so you're able to hear our voice. And this is just in a normal system. Like once you get into people that have hearing disorders, their system doesn't function optimally. And so those of us who have normal hearing, this is a pretty, like, you don't have to think about it. Your ear just does all of this stuff for you. And so as that video is playing, it's so cool because like our ears in that moment were doing those exact things on the basilar membrane, which is just mind-blowing.
Yeah. So essentially, the basilar membrane, every time you hear sound, it's represented on a different portion of the basilar membrane, and that's how you differentiate different sounds, and then it gets sent up to your brain. And so it vibrates in there, and your hair cells vibrate, and it's just really cool.
Quick? So back to the comic that we had at the very beginning. So this just shows like 20,000. So the reason why it was kind of funny because 50,000 we can't hear. So just as like a connection, that's what makes it really funny.
The range of human hearing is 20 to 20,000 hertz.
Yeah.
Are animals able to hear that 50,000?
Yes.
Some can.
So
yes.
the question was if animals were able to hear the 50,000. And so I always think of like dog whistles. Some animals do have the ability to hear much higher frequencies than we do, which is incredible. Yeah.
So the cochlea has 3 divisions in it. You have the scala vestibuli, which is on the top, the scala tympani, and the scala media, which is in between them both. You can see it here. And it's also called the cochlear duct. And they're just to keep it brief, they're just different divisions of the cochlea which house different parts so that it all works together. And the one that we are going to talk about is the scala media, or the cochlear duct, contains the organ of Corti, which is where your hair cells are located. And the hair cells are essentially what we call it dancing, because they move around when sound comes in, and that's what fires in synapses to send information to your brain. And let's see.
So we have a video. Is this the hair cell video?
Yes.
Okay, this is also super cool. So all of these little hair cells that are located in that pink portion that you see on the screen, those are the hair cells that can be damaged, possibly with lots of noise exposure, or they just wear down over time. And so this video is showing a dancing hair cell, and it's your hair cell responding to sound.
Yeah, think of it that all of your hair cells are doing this as we watch this video.
We get really excited about this.
So that's an actual hair cell from someone's ear.
Yeah.
I had no idea it looked like that.
Yeah, it's so
Like,
cool.
how many years have I been in like a profession? I have no idea. In my head, it's like,
Like hairs.
yeah, it's like cilia. You know, like in the ocean when there's like plant life on the bottom and it's like doing like this and wave with the ocean waves. That's in my head. That's what
Yeah.
it is.
Yeah, and there's so many, I don't remember the number of how many hair cells that you have, but there's like inner and outer hair cells, and you can go into depth just purely about hair cells, which is pretty incredible. Yeah. And here's some more about it. So again, the cochlea, the goal, it's the receptor organ of hearing. So all of this acoustic information coming in goes to mechanical, and then it comes into here. And these are the little hair cells that you just saw dancing. And there's a shearing action of the hair cells by the tectorial membrane, which is this purple object up here. And this is what sends the nerve impulses to the brain. So you'll see all of these have nerve fibers at the base of them, and then they all send information up to the brain from there. So when those hair cells start to break down, they're not going to be able to fire signals to the brain. And so that's why that's important, to keep your hair cells healthy.
You got a couple of questions.
Yeah, oh, questions, awesome.
So, for like, there's the three hair cells, do they each do they have different sounds? Or, so if like one was broken or ruptured or whatever, then would you not be able to hear a certain sound, or would it be a different, like,
Can we go to that picture really quick of the hair cells?
Yes,
I
the
think that would be
damaged
helpful.
ones.
Yeah, the damaged ones. So we'll show you really quick. I don't know where that's at.
It's like,
We're giving you a preview of all of our slides.
right here.
There we go. Okay, so this kind of shows you, so this is what your normal hair cells will look like. So there's outer and inner hair cells. And this is what the damaged hair cells look like. Yeah, do you want to go into more detail?
Essentially, so your inner hair cells and your outer hair cells are different based on function. So your outer hair cells, we call them the amplifiers. So when you hear soft sounds, your outer hair cells react and they basically make it louder. And your inner hair cells are sensory, so they're dealing with the connections to the brain. Now it's more based on what part of the cochlea or what part of the basilar membrane you have hair cell loss in. So what happens most of the time is you're going to get damaged hair cells in different regions of your basilar membrane, which would cause you to then have hearing loss in that region. So, for example,
I'm going back to the basilar membrane
noise
picture.
exposure usually happens at around 4,000 hertz. So you're damaging specifically the hair cells at 4,000 hertz, and then you have a hard time hearing 4,000 hertz and slightly around it. So it's not necessary, I mean, it is inner versus outer, but it's more based tonotopically on where the damage is occurring on the basilar membrane. And then it's usually damage to the outer hair cells, not to the inner hair cells, just because of their location. And that makes it so you can't hear it because the outer hair cells are amplifying the sound.
Yeah, and then just to show the low frequencies here at the apex and the high frequencies at the base, which is why I'll use the front door example really quick to explain this. So if you think about if you're walking in the front door every day, that doormat that's there is going to get a lot more wear compared to, say, like the doormat in the bedroom or something. Not that you'd have a doormat in the bedroom, but anyway, that's besides the point. So high frequencies are going to be worn a lot easier compared to the low frequencies, which is why high frequency hearing loss is pretty common to see, just because if you're walking through that front door every day, it's just going to get a lot more use compared to the low frequencies. But they're all used. Yes.
So is that why it's harder to usually hear like children and women?
Yes.
Correct.
You got it. And that, she just said that's why it's harder to hear children and women, because they have a higher frequency voice. Okay, where are we at here?
And that, like, normal age-related hearing loss generally is a high-frequency hearing loss, and they don't have as problems with the low frequencies.
Yeah. Great questions. All right, so that's that. Oh, a video. You want to show that video?
Yeah, we'll just show the 3-minute one of the...
This one?
Yeah.
Okay.
We're going to QWERTY.
So we like to show all those videos just to show you how intricate the system is and like how much your cochlea and how much your ear does, because it's pretty incredible. Talk about the pathway to the brain.
Yeah, so then we're going to briefly talk about what happens after that, because as we get more central, things get a lot more complicated. But essentially, so your peripheral system would be your outer, middle, and inner ear. And then after that, we're going to get into your central nervous system. And so From your cochlea, it's going to go to the auditory nerve and then the brainstem all the way up to your auditory cortex, which is in your brain. And essentially, this is where you're going to make use of the information that you're getting. So you can kind of see here, the cochlea is down here. It's just going to travel through, go all the way up to your auditory cortex. And we also call this Heschel's gyri, which is located in your temporal lobe. And then this is just one more picture for you here, just to kind of show you where it's at.
Does anyone have any questions about that? We won't go into detail about just the pathway because it's very intricate. No questions? Okay. So, hearing loss, which is the damaged system, basically. We'll kind of talk about this a little bit. So there's 3 different types. There's conductive, sensory neural, and then mixed. Conductive is usually a type of hearing loss that can be resolved. You can think about an ear infection, wax impaction, various different types of conductive hearing losses. Sensory neural, as this image shows, is kind of beyond so it's within the cochlea. So this is something that can't be fixed, really, unless with amplification, but it won't become a perfect system again. So this is where noise exposure, all of that damage occurs within this inner ear here. So conductive, this is a great, just a great image. Has sounds that are muffled or plugged. Ear canal blocked by wax is a great example. Hole in the eardrum, fluid, all of those things would be considered a conductive hearing loss. And then sensory neural is anything beyond this point. And then a mixed hearing loss is the mix of both. So someone could have both things going on, and we'd help resolve the conductive component. Yeah?
Where's the place that like a cochlear implant would help and where would it like not help?
So a cochlear implant, you know, I think a little bit more about this one, but the cochlear implant, there's electrodes that are placed within the cochlea. So this little structure here, there's just tiny electrodes. It kind of blows my mind. It gets wrapped around the cochlea, and then that's where that is placed. Can you talk more about that?
And so the thing with cochlear implants is they have to be, and I know that the guidelines, I'm not 100% familiar with the FDA regulations on it, but they basically have to be profoundly deaf. So it has to be like above a 90 decibel hearing loss for them to get, and they have to go through a series of tests because essentially they have to prove that they cannot benefit from traditional hearing aids or amplification devices to get a cochlear implant is essentially how that works. So it's kind of, it basically means like their inner ear doesn't function at all, and even if you put hearing aids on them, they're not going to hear any speech. And then you can put the cochlear implant in there, and it would, like she said, wire through the cochlea. And they also have to have,
No functional
they have to have like a cochlea, like because there's some, we won't go into it, but there's some other things where they wouldn't be able to get a cochlea because of like it was ossified, and they won't be able to fit it in there. So,
Yeah.
but yeah, basically they just have to have very profound hearing loss.
All right. And then severities, so mild to profound. And this will be covered by Dr. Sladen's lecture, but we just wanted to show you this right now so that way when he talks about it, it's a little bit more familiar. So mild to profound, you see this light blue line here. Basically anything above this point is considered to be normal. And then as you move down, that's going to be a more severe to profound hearing loss.
So have you all seen an audiogram before?
No. This is so exciting.
Okay, so this is what an audiogram looks like essentially, but with the colors to show. So from left to right are the pitches, so frequency, so low frequency to high frequency. And then starting from top, we go down. This is the decibels, so essentially how loud we have to turn it up before that person can just barely detect it. So you want to be up higher because that means that we didn't really have to turn it up for them to hear it. And again, we're just going to talk about it briefly because Dr. Sladen is going to come in on Thursday and talk a lot about hearing loss and how we test hearing, but just so that you understand that going down is worse because it's turning it up louder.
Okay. All right. And so there are various causes of hearing loss. We've talked about a few throughout this lecture: otitis media, so ear infections, perforation of the eardrum, medical abnormalities such as a growth or tumor, that kind of thing can be present. An inner ear, age-related hearing loss, so if your grandparents need hearing aids, that's probably what they have, presbycusis. There's noise-related hearing loss, which we've talked about as well. Ototoxicity, which that could be, so for example, someone who is receiving treatment for cancer or ototoxic drugs that are just they could have potential to harm the system. Genetic syndromes like Waardenburg's, which we're not going to go into detail on, infections, and then also things again such as tumors, auditory neuropathy spectrum disorder, which again we're not going to go into, but that's just kind of an overview of, there's all sorts of things that can cause hearing loss, and a wide range of ages as well could be impacted by all of these things.
Does anybody have any questions about any of these?
Does anyone have grandparents who have hearing aids? Awesome. Yep, that's very, very common. And that would be probably if they've had a lot of noise exposure over their lifetime or just age-related hearing loss. That's what we see a lot in the clinic. So we went over this a little bit.
Yep. That's a perforation. Again, just a bigger picture. And then right there is a vestibular schwannoma, or basically a tumor that would affect someone's hearing.
Yep.
So.
Is that a CT scan of the brain or of the?
So this is of the brain. So essentially, and there's different types.
Yeah.
So there's different central causes that can affect hearing, but with tumors or like acoustic neuromas, usually we would find them on their auditory nerve.
Yeah.
They can also be like on the brainstem and in other places, and then we would refer them out to get a CAT scan or an MRI, and so they would do imaging of the brain, and depending on the size, you would be able to see it, like which you can see right there. That's kind of a pretty decent size one.
So is that affecting the auditory cortex of the brain, or is that like compressing the nerve that's doing
Yeah.
That's a really great question. So a lot of times what happens is they're compressing the nerve, and the nerve, just most of the stuff that deals with auditory, the way that you hear, is somehow tonotopically organized. So for example, the nerve, just kind of throw it out there.
Yeah.
Yeah.
This is really in depth, but it's kind of cool.
Yeah, it's a bundle and it's layered. So you have, was it high frequencies
on the outside.
to then mid frequencies, and then the very middle is low frequencies. And so you notice it in the higher frequencies first, because if you have a tumor that's compressing the nerve, they're going to start to have high frequency hearing loss because it's going to kind of pinch that nerve. So yeah, she's like drawing it for you.
Just so you can see it. Middle frequencies. That's not an I, that's an E. Yeah, so this would be the nerve. So say, imagine like a tumor out here putting pressure on this nerve. The high frequencies will be impacted first, and the larger the tumor, the more impact it will have on those mid and lower frequencies as well. And I've had a couple of clients actually in the clinic who, I mean, I can't diagnose them, that's not necessarily our job, but all of the signs that I was doing for testing pointed to them having an acoustic neuroma. So we referred them to Bellingham Ear, Nose, and Throat, and just to try and get imaging done, and I never got the follow-up information on that, but we were kind of the first people who could be diagnosing this, which is pretty incredible. Yeah?
Does removing that tumor restore the hearing, or is it permanently lost once it's been compressed?
You want to go into it, or you want to?
It can. It's really hard to say because here's the thing with, I mean, I guess probably any tumors in general, but especially when you're dealing with nerves. So all the nerves in your brain, your brainstem, they're all very close together. And anytime that you have a tumor on a nerve, you have a chance of nicking the nerve when you remove it. And you also have a chance, so something that's actually really common is, so the facial nerve and the auditory nerve are really close together. So a lot of times what happens is when somebody has like an acoustic neuroma and they go in for surgery to remove it, they can actually get facial paralysis because they'll nick the facial nerve by accident. Because everything is so close together in your brainstem, all the nerves. So it's possible that it could help with their hearing, but it's possible that they could lose it altogether, or it's possible that it wouldn't change. It's really hard to say because they might remove it and it might just release the pressure of the pinching and suddenly they're okay. They might only be able to remove half of it, and so they might not get any worse, but they might be where they are, or they might nick something and they might lose it completely.
Yeah. And these tumors are slow growing as well, so some people decide to wait to have their tumor removed, but some people also want to get on it while it's small, so that way there's a better chance of removing it all. let's see. So this is just a recap. I know as a student I like to have recaps of the important information. So let me just put this all up here really quick. Okay, so recap. Outer ear, it's important for localization. That was that activity we did in the beginning. Earwax is produced there, and that's again for protective measures, so that way spiders don't go further in your ear. You'll always remember the spiders. That's important. Then the middle ear is to transmit the sound from out here via the lever action of the ossicles, and also pressure equalization of the eustachian tube. So making sure your ear is able to relieve that pressure by popping. So yawning, chewing, all of that will help relieve that pressure. Then the inner ear is important for hearing and balance. Then the sensory receptors in the cochlea are important to transmit sound to the brain. And then the brain is where you make sense of all the information. So I always like to say that you hear you hear in your brain, because without your brain, you can't do that. Which I know that sounds silly, but it's important to know though that it's not just your ear that's doing all the work. Your brain and those pathways need to be functioning, and they need to be healthy in order to be able to process the information that your ear is gathering. Do you have any more to add to the recap?
No, I think that was great.
That was pretty quick, but
Yeah.
just so that you guys can look at this, it's on, I think, the slides that were posted. It's just really helpful to look at.